Okay, so you know that feeling you get right when a wild guess turns out to be, like, totally spot on?
Oh, yeah.
Like, think back to 1979 when Voyager 1 was, heading out towards Jupiter, and that
Right.
moon Io.
Yeah.
Scientists had this, like, hunch, right? A really strong suspicion,
Mhm.
just based on how Io was getting tugged around by Jupiter's gravity, that it would be, like, incredibly volcanically active.
Right.
And then, boom, we got the pictures, plumes erupting
Wow.
hundreds of miles out into space.
That's incredible.
That moment of prediction becoming reality,
Yeah.
it's pure scientific gold.
Oh, for sure.
And that same buzz, that same anticipation of discovery is exactly what we're tuning into today
Okay.
as we look at a small world orbiting a star light years away.
I like it.
So this world,
Yeah, this world is L9859b.
L9859b.
It's a sub-Earth-sized exoplanet
Okay.
circling a nearby M-dwarf star.
M-dwarf. Okay.
Now, what's really got scientists excited
What's that?
are recent whispers hints from our cosmic detective, the James Webb Space Telescope,
JWST.
suggesting this little rocky world might actually have a volcanic atmosphere.
Okay, so a volcanic atmosphere on a rocky planet around an M-dwarf.
Yeah.
For you following along at home, you know that M-dwarfs, these small, cool, reddish stars that are actually
Yeah.
the most common type in our galaxy,
Yeah, M-dwarfs everywhere.
are notorious for making life difficult,
Yes.
for their planets to hold on to any air.
It's true.
They're like cosmic toddlers just throwing tantrums of high-energy radiation
Oh, yeah.
that can just strip away atmospheres.
They can completely strip them away. Yeah.
So the idea that this little L9859b might have a dynamic,
Right.
actively spewing volcanic atmosphere
Yeah.
in the face of all that
It's kind of amazing.
is genuinely thrilling.
Yeah.
Our deep dive today is all about the evidence
Yes.
that's been bubbling up mainly from JWST observations pointing
Yeah.
in that direction.
I'm like,
We'll be unpacking the findings from a recent paper titled Evidence for a Volcanic Atmosphere on the Sub-Earth L9859b,
catchy titles.
and some of the exciting preprints that have been digging into the nuts and bolts
Yeah, the details.
of these observations.
For sure.
So your mission, should you choose to accept it,
I think I will.
is to get to grips with this evidence.
Okay, I'm ready.
What clues are telling scientists that L9859b might be rocking a volcanic atmosphere, and why should we even care?
Yeah, good question.
What does this tell us about this planet's fiery interior,
Right.
and zooming out our whole understanding of what makes an exoplanet potentially interesting?
Interesting. Okay.
So let's tackle the big hurdle first.
Okay.
These M-dwarf stars.
Yes.
You mentioned their temperamental nature.
They are a little bit. Yeah.
Why does that generally spell trouble for rocky planets trying to keep their atmospheres intact?
Well, imagine a toddler having a tantrum, throwing high-energy toys everywhere.
I can see it.
That's kind of what young M-dwarfs do.
Yeah.
They blast out a lot of intense radiation,
Okay.
especially X-rays and extreme ultraviolet
Yeah,
XUV radiation.
Yeah.
When this energy hits a planet's upper atmosphere,
Oh.
it's like giving those atmospheric gases a supercharged boost. Enough energy for them to escape the planet's gravity
Oh, wow.
and just poof into space
It's gone.
over vast stretches of time.
Yeah.
This relentless erosion can completely strip
Wow.
smaller planets like L9859b of their precious air.
So no chance for an atmosphere?
Well, not necessarily.
Okay.
This is where the concept of volcanic outgassing becomes so vital.
Okay, outgassing, tell me more.
The thinking goes that if a planet has a significant source of internal heat,
Okay.
maybe from the gravitational pull of its star, constantly squeezing and stretching it.
So like tides.
Yeah, a process called tidal heating.
Tidal heating, okay.
That heat can fuel volcanic activity. And those volcanoes act like planetary burp valves, releasing gases trapped inside back into the atmosphere,
Interesting.
potentially counteracting that atmospheric loss we just talked about.
So a way to replenish what's being lost?
Exactly, replenishing air.
I'm following you.
Good.
Here's where things get really interesting.
Okay, go on.
Because LM9859 isn't a complete stranger to the Webb telescope.
That's right.
We've actually had a look at its planetary siblings.
Yeah, we have.
Planets C and D.
C and D.
What did those observations reveal?
Okay, well,
And how does little brother B fit into the family portrait?
yes, recent JWST observations of L9859C and D
Okay.
have given us some crucial context
All right.
for planet C, which is a bit bigger than Earth.
Huh.
The data essentially ruled out
What?
thick, puffy atmospheres
Okay.
made mainly of methane or even super dense atmospheres.
So a range of possibilities.
Yeah, a range planet D, which is larger still.
Okay, even larger.
It's more of a hybrid, not purely rocky. Likely with a significant envelope of lighter stuff.
Like what kind of stuff?
Like hydrogen, helium,
okay,
and maybe a lot of water. Intriguingly,
yes,
there were hints of sulfur in Planet D's atmosphere. Kind of environment where sulfur dioxide, SO2 could potentially form through chemical reactions driven by starlight.
Interesting. So Planet D might have a whiff of sulfur.
Maybe a whiff.
Yeah. But it's not the small rocky world.
Right.
With a potentially volcanically maintained atmosphere that we're laser focused on today.
That's right.
That brings us back to L9859b.
Back to B.
The innermost planet.
Yeah, the one closest to the star.
And the one that really sparked this volcanic atmosphere hypothesis. Even Hubble had a peek at it before JWST.
Yeah, Hubble did take a look.
What does Hubble tell us back then?
Well, Hubble's observations of L9859b were important for setting some initial boundaries.
Okay, what kind of boundaries?
It was able to say, okay, definitely not a clear, puffy atmosphere dominated by hydrogen.
So kind of ruling things out.
Yeah, ruling some things out.
Yeah.
But crucially,
yes,
it couldn't rule out denser atmospheres.
Okay, denser.
Made of heavier molecules.
All right, so still some possibilities there.
Yes, possibilities for sure.
Okay.
So L9859b remained a prime suspect for having a secondary atmosphere.
A secondary atmosphere.
One that could be constantly replenished by volcanic activity.
Okay, that's what we're hoping for.
Right, exactly.
And that sets the stage for the main event.
Okay, here we go.
JWST turning its incredibly sensitive eye towards L9859b.
Time for the big show.
Walk us through what Webb actually saw.
All right, so as part of one of JWST's early science programs, they observed four
what?
separate instances of L9859b passing in front of its star.
Okay, passing in front.
Yeah, these are called transits.
Transits, right.
They observed 4 transits using the near-infrared spectrograph.
Or NR.
NR spec, exactly.
All right.
Think of NR spec as Webb's superpowered prism.
Okay, a prism.
Able to spread starlight into its component colors.
Got it.
These observations took place in January and February of 2024.
Fairly recent then.
Yeah, pretty recent.
Okay.
The specific setting used was the G395H grating.
G395H.
Which allowed for a continuous sweep of colors or wavelengths. From 2.7 to 5.2 micrometers. With a tiny gap where the instrument's 2 detectors meet. This setup has a resolving power of about 2,700.
2,700, what is resolving power?
Meaning it can pick out incredibly fine details in the way the planet's atmosphere filters the starlight.
So very precise.
Very precise.
Okay, and they use something called the BOTS mode, right?
Yes, they do.
What's the significance of that?
So the Bright Object Time Series, BOTS mode, is specifically designed for looking at relatively bright targets, like this star and its transiting planet. Each observation session essentially captured
what?
The entire hour-long transit event.
The whole thing?
Plus a good chunk of time before and after.
So more than just the transit?
Yeah, almost another 2 hours total.
Wow, okay.
To get a really stable baseline of the star's normal light.
So you can compare?
Exactly, you need that comparison. And to help account for any tiny fluctuations.
And fluctuations in what?
In the instrument itself.
Oh, to make sure it's not the instrument.
Right, you have to rule that out.
Okay.
They took a whole series of individual exposures.
During each transit?
During each transit.
To do what?
To get a very precise measurement of the minuscule dimming of the star's light.
As the planet passes in front?
Exactly that tiny dimming.
Wow, that's incredible.
It is.
So they've got this treasure trove of data from these 4 transits.
That's right, a lot of data.
What's the next step?
Okay, so...
How do scientists go from these raw light measurements to figuring out if there's an atmosphere?
Right.
And if so, what's in it?
That is the big question.
It is?
The critical next step is like taking that raw data and refining it.
Okay, refining.
A process called data reduction and analysis.
Data reduction and analysis.
In this study, the researchers actually used 2
what?
Completely independent teams and software pipelines.
Okay, 2 different teams.
Called Eureka. And Firefly. To do this.
So 2 totally separate analyses.
Completely separate.
Okay, why do that?
Think of it like having 2 separate chefs trying the same recipe.
Okay, 2 chefs.
But with slightly different techniques.
Right.
If they both end up with a similar dish,
yes,
you could be much more confident in the recipe.
So it's like double checking.
Exactly, like double checking, yeah.
All right.
Both pipelines work to extract what's called the transmission spectrum.
The transmission spectrum.
Of the planet from the subtle dips in starlight during the transits.
Okay, I think I'm following.
This transmission spectrum is like a fingerprint of the atmosphere.
A fingerprint?
Showing which colors of starlight are absorbed more than others as they pass through the planet's gaseous envelope.
So if there is an atmosphere.
Right, if there is one.
And did these two independent chef teams?
Our chef teams.
Reach similar conclusions?
Encouragingly, yes.
Okay, good.
They found that the transmission spectra they got from both Eureka and Firefly showed a very good level of agreement.
Agreement, that's what we want.
Yes, that's good.
Across all 4 transits.
Yeah, all 4.
And both parts of the ANR-spec instrument.
Both parts.
That's very promising.
It is promising, yeah.
Okay, so they agree.
They do.
What does that tell us?
This gives scientists a much stronger feeling that what they're seeing is a real signal from the planet.
Okay, so it's not just noise.
Not just noise.
Yeah.
Not just some weird instrumental thing.
Right, we want to be sure that it's the planet.
Yes, that it's real.
Did they have any problems with the data?
They did have to wrestle with some tricky bits during the analysis.
Okay, like what?
Like very precisely fitting the curves of light.
Okay.
And accounting for tiny instrumental wiggles.
Wiggles.
Which can sometimes mimic a planetary signal.
Oh, so it could look like a planet is there.
When it's not, really.
Yeah. And it's just the instrument?
Just the instrument, yeah.
Tricky.
It is tricky.
So how did they deal with those wiggles?
For example, Eureka.
Okay.
Decided to trim some of the initial data points.
Okay, so cut off some data.
Just a little bit.
From a couple of the transits.
Yeah, just 2 of them.
To handle these little bumps.
Yeah, to smooth things out.
Okay, what about Firefly?
Well, Firefly used more sophisticated mathematical models.
Fancy math.
To try and factor out these noise patterns.
Okay, so 2 different approaches.
2 approaches, but they got similar results.
That's good.
It is.
Okay, so they've got these atmospheric fingerprints, these transmission spectra. How do you then interpret those fingerprints?
Okay, so
how do they figure out what kind of atmosphere would create that specific pattern of light absorption?
That's where they bring in the theoretical models.
Models, okay.
Think of it like having a library of known fingerprints for different gases.
Okay, so a database of what different gases look like.
Exactly.
Yeah.
They're light fingerprints.
Okay.
The researchers compared their observed spectrum.
The real data.
To a range of computer-generated spectra.
Okay.
For different atmospheric compositions.
Lots of different possibilities.
Lots of possibilities.
Okay.
They started with the simplest possibility.
Which is?
A planet with absolutely no atmosphere.
No atmosphere.
Just bare rock.
Just a rock.
In that case, all colors of starlight would pass through unchanged.
Okay.
Giving a flat transmission spectrum.
Flat. Okay.
They found that this no atmosphere model actually gave a reasonably good fit to the data.
Really?
At least according to one statistical measure called chi-squared.
Chi-squared.
Okay, so it wasn't a terrible fit.
So just a bare, airless rock wasn't entirely ruled out?
Not with absolute certainty.
Okay.
Based on that single statistical test.
So what do they do next?
So they moved on to consider more complex scenarios.
More complex, okay.
They compared their data to computer models of volcanic atmospheres.
Volcanic atmospheres.
Specifically ones that had been created by Seligman and colleagues.
Seligman, okay.
Earlier this year.
All right.
These models predicted what the transmission spectrum would look like for atmospheres rich in either sulfur dioxide,
SO2,
or carbon dioxide.
CO2.
In different mixtures.
Okay, so different amounts.
Different amounts, yeah.
Each.
Interestingly, the model that was almost pure SO2.
Almost pure, wow.
Around 98%.
98% SO2.
Showed a noticeably better fit to the actual observed data.
Than just the bare rock.
Yeah, than the airless planet model.
Fascinating. So a stinky, sulfurous atmosphere.
Yeah, you could say that.
Seemed to be a better match.
The better match.
Than no atmosphere at all.
That's what it looks like.
What other atmospheric possibilities did they explore?
They also used a really sophisticated tool.
Okay, what's that?
Called EPACRIS.
EPACRIS, what is that?
It stands for Exoplanet Atmospheric Chemistry and Radiative Interaction Simulator.
Okay, wow, that's a mouthful.
It is.
Well, what does it do?
This model doesn't just assume a list of gases.
Okay.
It actually calculates how those gases would chemically react with each other.
Oh, wow, so how they interact.
And how the temperature of the atmosphere would be structured.
Under the specific conditions of L9859b.
Exactly, taking everything into account.
So like the starlight,
The star lane?
And how much heat is escaping?
Yeah. All of that.
Okay.
This self-consistent model.
Self-consistent, okay.
Assuming an SO2-dominated atmosphere.
Right, SO2.
Also produced a good match to the observed transmission spectrum.
Another good sign.
Yeah, another good sign.
And crucially.
Yes. It predicted that such an atmosphere on L9859b would likely also contain significant amounts of sulfur trioxide.
Okay. SO3.
SO3.
Got it.
And even elemental sulfur in the form of S8, which could potentially cause a weird temperature inversion in the atmosphere.
A temperature inversion? What's that?
Getting warmer as you go higher.
Instead of colder.
Yeah. Which is unusual.
So multiple lines of theoretical modeling.
Multiple lines, yeah.
Seem to be pointing towards a sulfur dioxide-rich atmosphere.
It really does seem that way.
But just getting a decent fit isn't the final word, right?
Right. You need more than just a decent fit.
Okay.
That's where these Bayesian atmospheric retrievals come into play.
Bayesian atmospheric retrievals? That sounds complicated.
It is a bit complicated, but very powerful.
Okay, tell me more.
To really get a handle on how strong the evidence is.
How strong the evidence is.
For a particular type of atmosphere.
Right.
They use these advanced statistical techniques.
Advanced statistics.
Called Bayesian atmospheric retrievals.
Bayesian atmospheric retrieval.
They employed several different specialized software packages.
Different software, okay.
ExoTR.
Aurora.
And
Poseidon.
Poseidon. Wow, they have cool names. They do.
So what do these software packages do?
These tools allow researchers to explore a vast range of possible atmosphere compositions and properties and determine which ones are most likely to explain the observed data.
Okay.
While also giving a sense of the uncertainties involved.
So it's not just a yes or no?
No, it's more nuanced than that.
It's like, how sure are we?
Exactly. How sure are we?
Yeah, okay, let's unpack what each of these analyses found.
Okay.
Starting with ExoTR.
Okay, so using ExoTR on both the combined data from Hubble and JWST.
Okay.
And just on the JWST data by itself.
Okay.
The researchers found that models, including SO2.
SO2 again?
Yes, SO2.
Okay.
Were consistently favored.
Favored over what?
Over a simple flat line.
So over no atmosphere. Okay. How much was it favored?
Reaching a statistical significance of around 3.3 to 3.5 sigma.
3.3, 3.5 sigma. Okay, what does that mean?
Think of sigma as a measure of how confident a scientists are in a result.
Okay.
Higher sigma means more confidence.
So 3.5 is pretty good.
It's pretty good, yeah. It's interesting that when they tried adding things like clouds...
Oh, clouds would make it more complicated.
They would.
Okay.
Or accounting for potential variations on the star's surface.
Okay, so like star spots.
Exactly like star spots.
Okay.
It didn't significantly change the interpretation.
Towards something other than an SO2 atmosphere.
That's right. SO2, still the best fit.
Okay.
They also found that they couldn't really pin down
what?
the amounts of other gases like water and methane with the current data.
So we don't know about those?
Not yet.
Okay, and what about Aurora?
All right, so the Aurora analysis
Yeah.
also showed a preference for an atmosphere over no atmosphere.
Okay, that's consistent.
Yes, consistent with ExoTR.
With a significance reaching up to 3.6 sigma.
3.6, even a bit higher. Okay. And just like with ExoTR, SO2 popped up as the most likely absorber of light.
So again, SO2.
SO2 again.
With a preference of around 2.4 sigma.
2.4 for that one.
Okay.
The temperature they calculated for this atmosphere is consistent with what you expect.
With what you'd expect
for a planet at that distance from its star.
Okay, so the temperature makes sense.
It does, yeah.
Okay.
They also used a clever trick.
A trick? What kind of trick?
Called Bayesian leave one out cross-validation.
Okay.
Which is like testing how well the model predicts each individual data point.
So testing each point?
Yeah, one by one.
Instead of just the whole thing.
Right, exactly.
Okay, and what did that tell them?
This suggested that the parts of the spectrum where SO2 is known to absorb most strongly were the key drivers for preferring an atmosphere in the first place.
So SO2 is really driving that signal?
It seems to be, yeah.
And when they fed Aurora the self-consistent models from Epacris.
Right, taking those models.
Yeah.
They got pretty tight constraints on how much SO2 might be there.
How much?
Around 97 to 98%.
Wow, 98% SO2.
Pretty intense.
It is intense, okay.
And finally, what did Poseidon tell us?
Poseidon, yeah.
The Poseidon analysis also leans slightly towards an atmosphere model.
Okay, towards an atmosphere.
Compared to a bare rock.
Just a rock.
Or a scenario where the star itself was causing some weird signal.
The star itself.
Yeah, sometimes stars can be tricky.
Okay.
They highlighted that the roughly 2 sigma preference
2 sigma, yeah.
for an SO2-containing atmosphere seemed to come from specific absorption features in the observed spectrum.
Specific features, okay.
The results also suggested that thick atmospheres made of lighter gases were unlikely.
So ruling some things out.
Yes, ruling those out.
And again, the best fit was an atmosphere packed with SO2.
Packed with SO2, it seems to be the theme.
It really does.
Yeah.
So across the board?
Yeah, across the board.
These independent teams, using different statistical tools.
Different tools.
Different teams. Are all pointing towards an atmosphere?
That's right.
And sulfur dioxide seems to be the main ingredient.
The main ingredient, yeah.
Okay, so let's imagine for a moment.
Okay, let's imagine
that L9859b really does have this stinky, SO2-rich atmosphere.
Okay, it's stinky, but interesting.
It is interesting. What are the big implications?
Big implications, all right.
What does that tell us about the planet itself?
Well, the implications are quite significant.
Okay, I'm ready.
First off, in terms of the atmosphere's chemistry.
Okay.
An SO2-dominated atmosphere at the temperatures expected on L9859b could actually stick around for a while, relatively speaking.
Stick around so it's not immediately lost.
No, not immediately.
Okay, that's good.
Before being broken down by starlight.
Starlight will break it down eventually.
Eventually, yeah.
Okay.
And as those self-consistent models showed,
right,
we'd expect to see other sulfur-based molecules like SO3.
SO3, okay.
And even S8 hanging around.
So a mix of sulfur stuff.
A sulfur cocktail.
Okay. And what about the long-term survival of such an atmosphere?
Yes, the long-term survival.
Given that angry M-dwarf next door.
Right, the angry M-dwarf.
That's a really crucial question.
It is a crucial question.
So is it going to survive?
An SO2 atmosphere like this wouldn't last forever.
Okay.
If there wasn't something constantly replenishing it.
It needs replenishing.
It does.
Okay.
Estimates suggest that without a source, an atmosphere with a pressure 10 times that of Earth's
10 times
would only last about 10 million years.
10 million years, that's not very long.
In astronomical terms, no.
Before being lost to space.
Gone.
So what does that tell us?
This strongly implies that if this atmosphere exists,
if it exists,
it must be in a sort of equilibrium.
Equilibrium, okay.
Where volcanoes are constantly spewing out SO2.
Constantly spewing.
At a rate that balances how much is being lost to space.
So it's like a constant battle.
A constant battle, yeah, between loss and replenishment.
Okay. That sounds like a planet with some serious plumbing issues.
It does a bit, yeah.
Constantly venting.
Constantly venting.
Can we even guess how much volcanic activity would be needed to keep that up?
The researchers actually did try to make an estimate.
Okay.
If we assume that the molten rock inside L9859b
they're molten rock,
has a similar amount of volatile elements.
Volatile elements.
As Earth mantle.
Okay, so similar stuff inside.
Similar stuff, yeah.
Okay.
They calculated that the planet would need to have volcanic eruptions happening.
Okay.
At a rate significantly higher.
Higher than what?
Than that of Io. Jupiter's incredibly volcanic moon.
Io is very volcanic.
Extremely volcanic.
Okay, and this would have to be even more.
Maybe about 8 times higher.
8 times higher, wow.
Per unit of mass.
So a lot of volcanism.
A huge amount, yeah.
Wow, that's a truly staggering amount of internal heat being released.
It is a lot of heat.
Which then has knock-on effects for what's going on inside the planet, right?
Absolutely.
So what's happening inside?
That level of volcanic activity almost certainly points
to what?
A significant amount of tidal heating.
Tidal heating, so the squeezing and stretching.
The squeezing and stretching.
From the star.
Yeah, the star's gravity, generated by the constant gravitational tug from its star.
Right.
The researchers were able to put an upper limit on the planet's tidal quality factor.
Tidal quality factor.
Which essentially tells us how efficiently it converts.
Converts what?
That gravitational energy into heat.
Oh, okay.
Their calculations suggest a value.
Yeah,